Alright, let's take a moment and talk about the mean value theorem. Mean value theorem says if there's a differentiable function on some interval from a to b, and it's continuous at the endpoints of the interval, then there exists a c value somewhere on the interval such that when you construct a line between a and b, and you find the slope of that line, which would be f of b minus f of a over b minus a, then there exists some c value in the interval where the derivative at your c value has the same slope as the line between points A and B. I love the picture to this because it's not hard to argue that these slopes at least look the same, because to me they look like parallel lines, and we know parallel lines have the same slope. And so a lot of times the mean value theorem will ask us to find a particular c value. So I thought we'd take a moment and do a quick example of the mean value theorem in action. So let's define a function. Let's let f of x equal a quadratic. We'll do x minus 3 squared minus 1. And we'll draw a quick sketch of this. And I put it in vertex form just to make our life a little bit easier. So we'll do a couple hash marks here. We'll go down 1, 2, 3, 4, yep, 5. And so our vertex for this is going to be at positive 3, 1, 2, 3, negative 1. And parabola is going to go up here a little bit. And then maybe up a little higher. And we'll connect our dots. And freehand in this, so bear with me. And we'll put a little axis of symmetry in there. Add a little flare. We got our negative 1 down here. Okay, so when we're asked a mean value theorem question, the question might say something like, find the c value on the interval and we'll come up with an interval here. Maybe it'll be 2 to 5 that satisfies the MVT, the mean value theorem. So we want to find some c, and c will be somewhere between 2 and 5, so somewhere in this area. And remember that we want to make sure that the slope between our endpoints, in this case between 5 and 2, is equal to the derivative of our function at some value c. It's our job to find the c value that makes this statement true. Okay. A visual of what we're trying to find is if we construct a line between 5 and 2. I don't like this fact that that's the same color. Sorry, guys. Then I want to find where is the parallel line to this. So the first thing I'm going to try to find is this slope. And I need f of 5 and I need f of 2. And I don't trust my graph completely. Looks like f of 2 is going to be 0, but just to confirm, f of 5 is going to be this function up here, evaluated at 5, which would be 5 minus 3 squared minus 1. So we've got 2 squared minus 1. Looks like we have 3. So f of 5 is 3. F of 5, 1, 2, 3. All right, we're in good shape. And f of 2 is going to be 2 minus 3 squared minus 1. And we got negative 1 squared minus 1, and it is 0. So it looks like our graph actually looks pretty good. So if we substitute these values in, we have a 3 minus 0 over 3. That's my 5 minus 2. And so the slope of this orangish line is 1. You know, rise over run, just straight up algebra. And so we need to find the f prime. We need to find where the derivative is equal to 1. So I'm almost done. I'm going to go back up here to my function, and I need to find f prime of x. And f prime is just going to be 2 times x minus 3 to the first. There is a chain rule in there. Maybe you want to write it, maybe you don't, because the chain is just 1. And then the derivative of a constant 0. And so I have that my f prime is equal to 2x minus 6. And to close the deal, I want my derivative to be equal to this slope. So last step, I set my derivative equal to 1. And I'm going to add 6 to both sides. I'm going to divide both sides by 2. And I get 7/2. And we say, what is 7/2? All right, 7/2 is the x value. 7/2, you know, is about right here. And if we go down to right here, it's a little deceiving because, you know, this x value, c, is usually described as a specific x value. So this x that we found is our c. That is the answer. That is the c that satisfies the MVT. Man, lots of variables in this. But if we want to confirm it visually, if we, you know, construct a tangent line right here, and this isn't even that great of a sketch, but it looks parallel, which makes me think I'm sane. So anyway, there's the mean value theorem. Hope you enjoyed.